What's up? We will be doing the momentum question today. I've extracted all of the times they have asked on momentum since 2020. It's when they introduced it to this paper. And yeah, up to 2022, so it's 3 years, and I've answered them all for you. A 40-page long worksheet. So that's a really good resource. Make sure you download that and start to go through it. We'll be going through 3 different questions today. 2 relatively simple momentum questions, but gives you a good taste of how they usually like to ask it. And then the third question will be a harder one, a more complex momentum example. What is momentum? Well, just like energy, momentum is conserved. So the initial momentum, the momentum of the masses or particles or whatever before an interaction, usually always a collision, will equal the momentum after the collision. And momentum is the mass of the object times the velocity which is moving. And I give a general example here so you can see. So it's just basically saying the momentums of the initial particles M1, M2 before the collision is equal to the momentum of the particles after the collision. Momentum is conserved. Okay, and that's it. That's all you need to know. So just momentum is mass times velocity, and I'll show you exactly how we do that here. Let's do some questions. So they will ask a question on this. It's come out every single year in the last 3 years. So it's gonna come out. But after you've done that worksheet, watch this video, you're gonna be laughing. 2 particles P and Q have masses 0.2 and 0.5 kilograms respectively, and are on rest. And it's usually like this. It'll be on some smooth horizontal plane. So we just draw this out really quick. So we have particle P and particle Q, where the mass of P is 0.2 kilograms and the mass of Q is 0.5 kilograms. P is projected towards Q with a speed of 2 meters per second. So P moves towards Q, which is at rest. This isn't moving at 2 meters per second. Write down the momentum for P. This is very easy. We can just substitute into the momentum formula. Momentum equals mass times velocity. And in the case of P, this will be the mass of P times the velocity of P, which equals 0.2 to 0.4. And the units will be, if you're ever unsure about the units, you can always write it in SI base units. It's just kgs, mass times meters per second, velocity, kg, meters per second. So the momentum of particle P is 0.4 kilogram meters per second. B. After the collision, so these things collide. I like to do it like this. I say, okay, this is like a collision line. So this is before and this is going to be after. After they collide, P continues to move in the same direction with a speed of 0.3 meters per second. So it's important to take in direction because it will affect the sign of your momentum. In 0.3, so P moves at 0.3 meters per second. Q, because it's at rest, it's going to start moving this way, but we don't know what it is, so it's VQ, sorry. It wants us to find the speed of Q after the collision. Right, so these things, Q is at rest, this thing is hit by P, and then P starts moving at 0.3, and then Q will go off at some velocity, which we're going to find out. Well, momentum is conserved. That means the momentum before the collision and after the collision are the same. So we can say momentum of P, U. Okay, so I usually write it like this. So the initial speeds, so the speeds before the collision, UP equals to 2 meters per second. UQ equals to 0 meters per second because it's at rest. And VP equals to 0.3 meters per second. And VQ, we don't know, but we want to find. So momentum is conserved. Momentum is conserved. So we can say that MP UP plus MQ UQ, the momentum of P before the collision, and the momentum of Q before the collision equals to the momentum of P after the collision plus the momentum of Q after the collision. All right, this is the speed of Q, P after the collision, and the speed of Q after the collision. Okay, so we just plug these values in. We get 2 multiply the mass of P, which is 0.2. So 0.2 multiplied by 2, which we already found before, plus this would be the mass of Q times 0. And anyway, 0.5 times 0, so which is 0, equals the mass of P, which is 0.2, times V after, which was 0.3, plus the mass of Q is 0.5 times VQ, which we're trying to find. So this will be 0. What do we get? Therefore, we get 0.4 equals to 0.2. 0.2 times 0.3, 0.06. 0.06 plus 0.5 VQ. So therefore, 0.5 VQ will equal to what? 0.3634. So VQ should be this divided by 0.5. 0.68 meters. 68 meters per second. Okay, so that's the velocity of Q after the collision. This. It's a basic example, but it gives you an introduction to momentum. We'll do another one where there's some unknowns now, but it's the same. So two spheres A and B equal radii, masses, so the mass of A equals to A times m kilograms. The mass of B is equal to m kilograms, and where K is greater than 1, so that means the mass of A will be greater than the mass of B, are free to move a horizontal plane. A is moving towards B with 6 meters per second, and B is moving towards A at 2 meters per second. Okay, so we'll look at what's going on. So we have A, and we have B, and it's a smooth surface, so there's no friction involved. It's important. So if A is traveling at 6 meters per second, well, it's going to be traveling at 6 meters per second forever. It's a smooth surface. There's nothing slowing it down. It's a completely hypothetical scenario. There is no such thing as a completely smooth surface, unless we go into some alternate universe. I don't want to be on that surface. Okay, so A is moving towards B with 6 meters per second, and B is moving towards A at 2 meters per second. After the collision, A and B coalesce, which means they come together. So, and after the collision, the speed of, so remember it is saying speed, but I'm notating direction here. So 2 meters per second. So this will be, UA for the collision here is 6 meters per second, but UB is minus 2 meters per second, right? Because it's acting in the opposite direction. Left is negative. And so they coalesce, so they come together and they stay together and they start moving together like a happy, loving couple. So they move together forever along this smooth surface at a speed of 2 meters per second. And it will be this way. So it'll be positive because, this is moving at a big higher speed as B, and it also has a bigger momentum. So it's gonna go that way. If it was the other way around, then it would be, if A was going 6 meters per second this way and B was going, then it would be going this way. And then this would be a negative velocity, but it's not. So this is 4 meters per second. Okay, and so our V final, so I'm calling this the total thing, which is also the velocity of A, the velocity of A after the collision, the velocity of B of collision. Just put them together. It's 4 meters per second. So we can say, if we want to find K, the momentum before equals the momentum after. So MAUA plus MBUB equals to the mass total of both of these things times the final velocity. Right? You could do the same as before, but you could say be the mass of A times the velocity of A, right? Plus the mass of B times the velocity of B, the final velocity of B. But this is 4, and this is going to be the total mass. So if we just, it's going to be this thing going to be the same as, it's just the total momentum of this coalesced object. Okay, so the mass of A is km. U is 6, plus the mass of B is m times -2 equals the mass of T will just be the mass of A plus the mass of B, is km plus m times 4. Okay, this will give us 6km minus 2m equals to 4km plus 4m. The m's will all cancel. Divide through by m, so we get 6k minus 2 equals to 4k plus 4. Take that over, we get 2k equals to 6. So therefore, k equals to 3. Find in terms of m the loss of kinetic energy. They asked this a lot. So B, you know that the change in kinetic energy from before to after the collision will simply be the final kinetic energy minus the initial kinetic energy. If we find the change in kinetic energy, we can find what the loss in kinetic energy is. So therefore, what is the final kinetic energy? Well, that's just going to be the kinetic energy of this final object, which is just a half the mass total times the V final squared, which equals to a half. Now K is 3, so our total mass will just be 3m plus m, which is 4m. 4m times V velocity final, which is 4 squared. So that equals to 4 squared times 4 divided by 2, which is 32m. This is 32m joules. Okay, initial just be the kinetic energy of A plus the kinetic energy of B. This is half the mass of A times UA squared plus half. This is just the velocity of A before the collision plus MB UB squared. This is half the mass of A plus Km. Okay, it's 3. So this would be a half of 3m times the velocity of 6. No, 6 squared plus a half m mass of B times minus 2 squared. So this equals to 6 squared times 3 divided by 2, 54. 54 plus, would be 4 divided by 2 plus 2, 4m plus 2m, which is 56m. So therefore, the change in kinetic energy for this collision is going to be the final, which is 32m, minus the initial, which is 56m. The change in kinetic energy is minus 24m joules. So therefore, if the change in kinetic energy is minus 24 joules, then the loss in kinetic energy is 24m joules. Right, it's changing negative, so it's losing 24. If it was positive, then it's gaining 24. But in a collision, it'll never be positive. Okay, cool. So that's just, it's again similar as the first question, but it's just now we've got some M's and K's and stuff, so it spices it up a little bit, but you're not doing anything different. Okay, and finally we'll do this one, and this one is on the harder end of these momentum questions, because you're having to involve other knowledge of forces and kinematics and stuff like that. And really, in these mechanics questions, the hardest questions are the questions with where you involve a lot of stuff. So you're involving lots of different topics all together, and you're having to use all your knowledge from all of them. But if you understand all the topics individually, then you can bring them all together very nicely, which is exactly what we're doing in this series. So this shouldn't be too difficult. So it's everything you know, but plus momentum. Okay, so a particle P lying on a smooth plane. So this is smooth plane, so no frictional force, 30 degrees. So it's just explaining this thing out. Particle Q, this lies at rest. Equalize with Q. Okay, so let's just draw this out, as I like to do. Okay, this is theta, and theta is 30 degrees. Let's call this distance here, so this is our P. This distance between here and here was D1, and our D1 is 2.5 meters per second, and then between the base here, I guess I'll do it. The base here is D2, and Q is 1.5. I always recommend drawing these things out, even if they give it to you, because it just reinforces what's going on in your mind. Because sometimes these harder ones can get complicated because there's a lot going on. So doing sketches is really helpful. What else do we know? We know that the mass of P is 0.3 kilograms, and the mass of Q is 0.2 kilograms. Okay, and that's all the information they give us. And we know this is a smooth surface. It is given that the horizontal plane is smooth, that after P continues moving in the same direction, after the collision, P continues moving in the same direction with 2 meters per second. Find the speed of Q. Okay, so if we just get an idea, so this thing is going to roll down this hill, gain speed because it's going to be accelerating down the hill. Then when it gets to here, it's going to be moving at some speed. And then because it's a smooth surface, when it collides, it'll be moving at the same speed. And when after it collides, where P moves at this, and we want to know what at 2 meters per second, we want to know what Q moves at. So, if we just do a rough idea here, for this bottom part of the plane, there's going to be some speed which we don't know, some speed here that P has. Some speed here that P has. And it's going to make it collide with Q, which is at rest. And then after that collision, P is moving at 2 meters per second. And we want to know what Q is moving at. So this will be our UP, whatever this speed is, and this will be, so then we can just use our momentum equation to find that. But first we need to find what the speed of P is at the bottom of the slope. So we can do that because I guess this comes down to your understanding of forces. So what is the speed of P at the bottom of the slope? Well, it's got its weight here. So if we want the sum of the forces of P, this is a little overkill, but is going to equal to the mass of P times the acceleration of P down the slope, right? So this forces here is just going to be the weight of P down the slope, right? Which is just W sine theta, right? So I'll call it Fg. The weight of P is MPa. This is mg, right? The weight of P. This is mg sine theta equals MPa. So therefore A equals to g sine theta. It's 10 sine of 30 degrees, which is 10 times 30, it's 5 meters per second squared. So P is accelerating down the slope at A equals 5 meters per second squared. Okay, and it's traveling a distance, call it S, which will be D1. It's traveling a distance of 2.5, is it? 2.5 meters. Okay, so it's kind of like a side note. Sorry if this is a little messy. So the speed at the bottom of the slope will be from V. We have the initial speed, because it starts at rest, is 0 meters per second. At the top of the slope, we have the acceleration down the slope is positive 5 meters per second squared. And we have the displacement of this object to the bottom of the slope will be 2.5 meters. And we want to know what the final velocity is. So then we can know what the velocity of P is when it collides with Q. So as V squared plus V squared is from kinematics, U squared plus 2as. We get 0 squared plus 2 times 5 times 2.5. That's going to equal what? 2 is supposed to be 25. So therefore v at the bottom of the slope, so this will be the square root of this, which is 5 meters per second. The velocity at the bottom of the slope will be 5 meters per second. So therefore, the velocity before the collision will be 5 meters per second. Smooth, so it's just traveling, it's going to hit it at the same speed. Right, so therefore, you can say we have before the collision, velocity of p is 5 meters per second. Velocity of q before the collision is 0 meters per second, right? Because it's at rest here. And then after the collision, the velocity of p is 2 meters per second. And the velocity of q is what we wanted to find. Speed of q after the collision. Okay, then we just plug it into this equation, the conservation of momentum equation. So mp up plus mq uq equals to p mass of p times velocity of p plus mq vq. Masses of these two things are 0.3 and 0.2. So this is, therefore we get 0.3 times u, which is 5, which we found before, plus mq, which was 0.2. We'll check that because your boy can't remember shit. 0.2 times 0, so it doesn't matter. And then 0.3 times vp, which is 2, plus q, which is 2 vq. That's 0. Take this over, so we're going to get 0.2 vq of this minus this. 3 times 5 minus 2. And 0.9. So therefore VQ 4.5 meters per second. Okay, so the reason that's difficult is because you're having to use a lot of different things. You know, we're using forces to calculate the acceleration down the slope, and then we're using kinematics to find the velocity at the bottom of the slope, and then we're using momentum to find the velocity of q after the collision. And so that's why it's 5 marks. Okay. Apology if that was a little messy, maybe. I'm just trying to explain all of it, you know? I'm not trying to be super clean, I'm trying to explain all the things individually. Just my teaching style, probably. It's given that instead that the horizontal plane is rough, and when P and Q collide, they coalesce and move at speed 1.2 meters per second. Find the coefficient of friction between P and the horizontal plane. Okay, so now it's saying that this surface, so we have our P here, which is moving at 5 meters per second, you know, at the bottom of the slope. But now this surface is rough now, and it has a mu, which we, like a frictional coefficient, which we want to find. This is rough, so this is going to experience P is going to experience this frictional force, right? And we still have our Q here, which is at a distance of d2, which was what, 1.5 meters. Then they collide, and when they collide, they coalesce, and then they move together at a speed of v final, which is 1.2 meters per second. Okay, just to make sure. So it's given the horizontal plane is rough, and when P and Q collide, they coalesce. So it's just saying the horizontal plane, so not this part. So it stays the same. So it's going to, the speed at the end of the slope, downward slope, is going to be 5 meters per second for P. So they coalesce between 1.25. Okay, so we have then before the collision, speed of P is this. speed of q is this. And after the collision, our v final is 1.2 meters per second. But, so actually, hold up. So at the bottom of the slope, it's 5 meters per second, right? But when it reaches it, it won't be 5 meters per second because now it has a frictional force acting on it. Before it had no frictional force. So we could just say at the bottom of the slope, the speed will be the same here as when it collides. But now we can't say that. So we don't actually know what UP is. The initial speed, the speed just before it collides. So we're going to need to find that. And how do we find that? Well, we're going to need to find this frictional force, find the deacceleration, and then use kinematic equations to find the final velocity, similar to what we did before. So with this object here, we can say that for P, the sum of the forces of P is going to equal to the mass of P times the acceleration, in this case deacceleration. This will be minus, this is acting opposite to the velocity or the direction of the motion, minus F mu equals to MPa. What is F mu? This is just minus mu r, where this is the normal contact force. I have a video on this. And r is going to just equal to the weight, which is mg. Right, so this is minus mu mass p times g equals mpa. These will cancel and we get the acceleration, or the deacceleration, is equal to minus mu g. So that's g is 10, so we can say it's minus 10 mu meters per second squared. So this object, P, is deaccelerating minus 10 mu meters per second squared along this horizontal plane. So we have the acceleration, we have the initial velocity, which is 5 meters per second. We want the final velocity. We have the acceleration. And we have the displacement of this object, which is 1.5 meters. So with all these, we can say that v squared equals u squared plus 2as. So we get 5 squared plus 2 times minus 10 mu times s, which is 5. That gives us 25. 2 times negative 10 times negative 10. 30 negative mu minus 30 mu. So therefore, the velocity just before it hits the q is going to be the square root of 25 minus 30 mu meters per second. So therefore, just before it hits, so we can say just before it hits, the velocity of p is this, up, where up is square root of 25 minus 30 mu meters per second. UQ is 0, right? And after the collision, they move together with speed of VF, where VF was 2 meters per second, I'm sure. .2. And the mass of P was 0.3 and the mass of Q is 0.2. Just double check that. 0.3. Okay, so now we can set up the momentum equation and find mu. So we have mass of P times velocity before the collision of P, mass of Q times velocity of Q before the collision, and then the mass total times the final velocity. This is equal to, the mass of P is 0.3 multiplied by the square root of 25 minus 30 mu plus the mass of Q times U, which is 0, so this is just going to be 0, equals the total mass, which is 0.5 times 1.2. Therefore, we get the square root of 25 minus 30 mu equals to this divided by 0.3. So 0.5 times 1.2 divided by 0.3 is 2.5. Zero point 2, 0.3. It's 2, not 2.5. And then we get 20, so therefore 25 minus 30 mu equals 4. Therefore we get 30 mu equals to 21. Mu equals to 21 over 30 is 21 divided by 7. And that's your answer. So that was a rather, I would say, difficult one, and this does pop up from time to time, difficult ones, because they're getting to use lots of different things. But with something like that, we have to, you might not know where to start. Like, okay, well, how do I calculate the coefficient friction? Well, there's a collision, so you're going to have to use the momentum equation. So set up the momentum equation, and you would see, okay, well, the thing that I need is UP. So this velocity before the thing. Well, how do I find it? Well, I went through and I said, okay, well, it's deaccelerating, so I'm going to find UP. I found UP, and then it was in terms of mu. So then I could sub that back into that momentum equation and find mu, the coefficient of friction. That's it. Make sure you download this worksheet. It's really good. I've extracted all of the answers, all of the questions, and answered them all for you. There's a relatively, it can be difficult in those larger questions, and you have lots of examples of those, but majority of the time, like 70% of the time, they usually ask in simple cases things like this. You find the change in kinetic energy and stuff like that. It's not too difficult. Okay, that's it. Now I will be discussing the idea of conservation. This idea of conservation has propped up a few times for you in your exploration of mechanics, and I want to take a moment to discuss this idea from a more spiritual, I don't really like that word, but from a different sort of metaphysical angle, and how it can play into your own life. So what we see is that things like energy, momentum, properties are conserved, which means that, so before an interaction occurs, like we saw with those, let's say, two balls when they hit each other, and then they coalesce or they join and they merge together into a larger mass, there's a conservation happening there, but there's not, and nothing is being lost. There's just a change happening in its form. So you might, let's say, lose kinetic energy, but that's going into something else. So with everything, there's a conservation of energy, and so we're changing a form, like a physical form. So the ball will be larger when they come together, but there's a conservation between this, before the interaction occurs and after it. And so let's take you, for example. You have a lot of activity or energy happening within you, and so I'd like I've talked about before, you will change, and how you change, the activity and energy, which is so much, you have so much energy and things going on within you, this will be conserved. So so when you change, there'll be a change, and so you'll change form. So that could be psychological form, this could be emotional form, this could be physical form, but you're changing form and conserving that energy. And you can consciously and deliberately sort of mold yourself in that way. And we see this happens on an individual and also a collective level. There's a conservation of energy going on. We are creating things. Let's do an example. Let's say, for example, the pyramids, something like that. So you have a group of people creating the pyramids, the Egyptians or whatever. And so the collective energy is being transformed into a physical pyramid. And so there's a conservation of energy from the collective to a physical form, the pyramid. And I would say that that's a pretty good way to conserve that energy. We've collectively produced a monumental thing. It's a I don't know the ins and outs of the pyramids, but it's a pretty beautiful thing. And so collectively as humanity, and this is going really deep, what we want to be doing is we want to be conserving our energy, which we have, and transforming it in physical or mental or emotional or different ways to produce cultures, societies, and things in the world which are of higher form, like something like the pyramid, because we can transform the form of the world into lower level things which aren't beneficial for humanity and for each of us individually. And so this idea of conservation and conservation of energy is something which, when we think about, can be used, like, because it's such a universal phenomenon. The universe is conserving everything. It's conserving all of its energy. There's no energy being lost, it's simply transforming. And so using that idea, we can start to individually implement ways in which we can transform things in positive ways, which makes it more beneficial for people, more beautiful for surroundings, more all this good stuff. And if it's done in ways in which we're transforming in sort of what I would consider negative ways, then that reflects in the society and culture that we have. If we create forms and use this idea of conservation in negative ways, we're not deliberately thinking about it and trying to go to a higher ideal of creativity, then we get sort of like failed and sort of degrading societies that are degenerate, or they degenerate, they deteriorate, and they die. So it's actually very important that we transform this energy, which is conserved, in positive and creative ways, individually and collectively. Maybe that's pretty deep, but why not? Just talk about it. Something that I thought about while I was shooting this video. So I thought I'd take a minute to just outwardly flow some ideas that when I think about conservation for myself. Maybe it was useful, maybe it wasn't. It's just interesting. I find this stuff interesting and I like to talk about it. Anyway, hope this video was useful. If it was, you know what to do. Subscribe, like, and I'll see you when I see you.